Hello. Today I'm going to talk about AI applications in health. As we all see from the bombastic titles in journals and from media, we can expect solution for almost everything by AI. But is that really so? During this pandemic, it turned out that a beautiful collaborative efforts actually brought us many things which were done in much shorter time than it expected, and many people did many demonstrations of heroic action in that regard, but it seems like a lot of things were expected of algorithms when married with a big data. Majority of us also believed, and when somebody says, look, an algorithm resolved this and that, and basically those guys who are developing algorithms can tell you anything. And how you are going to check about that? Alan Turing Institute from UK actually did perform a large study to see who are the AI shining stars from the last period, but unfortunately they couldn't find those shining stars. Instead, they found a lot of problems. This is what we are talking about now. When somebody says AI, which is a buzzword, immediately comes to mind sci-fi interpretation of robots and solutions of the future which are still not here. And I have an impression that general public who is actually not involved in research has unrealistic expectation, to say the least. What is actually going on? I have to say that there are some really useful solutions coming from AI, like for example early detection of sarcoma or early changes on your retina if you have some disorder, or anything which comes with the processing of images. For example, early applications of AI were actually very useful in detailed reading of details of Röntgen scans or some other scans, because there is a reason for that. This task is actually boring to humans. And even if you're a specialist radiologist, you can be tired sometimes, you can be bored, and you skip some detail which machine can meticulously find. But what about other subjects? For example, in the area that I'm active in, which is computational psychiatry, things are a little bit more complicated. I will take on this, like we have industry here and real-life applications here, because if somebody who is, let's say, having some platform or some internet application of recognition of cats faces or human faces, this is one thing. And when you want to apply this algorithm, which is based and developed on web data, to really complicated problem like, say, detection of cancer and recommendation of the treatment, this is pretty far stretch, because you want to use algorithm which is developed on web data, and when you go to real life you expect to have the same performances. It is not going to work. So this is exactly what Alan Turing report says, that health issues are much more complicated and they have much more dimensions than spam filter task. I think that society is falsely believing that the algorithms that we are developing can work much better than it is actually the case. One of the examples is developing algorithm to learn from patients' data. But there is a problem. Medical data are highly dimensional and very complicated. For example, from looking in the voxels in one fMRI scan or MRI scan to recordings of the voice, you always have such a densely sampled data, and you have a large number of data per person. What is characteristic to applications in health is that you have usually small sample with high density data, meaning that you collect medical records, previous medication, lifestyle, maybe some neuroimaging findings, results of the tests, voice recognition, things like that. And you all merge all that and you're training algorithm to find certain links within those data. There is a problem with that. In statistical learning theory, there is so-called curse of dimensionality. That means that the larger number of features, especially in a small data set, is actually increasing the so-called blind spots. What are the blind spots? Let's say that you have one variable. If you have only one feature and you use that on a small data set, this is one-dimensional problem. When you have two features, this is two-dimensional problem. But with the rise of dimensionality of the problem, meaning how many features you have on the same sample, the sparsity of data is rising. What is the sparsity of data? This is what you have between two samples, because whatever physical phenomenon that you're measuring, you have samples over the time. But whatever you sample, you cannot sample every single thing. You have to have sample here, then after several samples you have there, and you have the distance between two samples. If you put that on one scale, this is one thing, the sparsity of data. But if you put it in 2D with two variables, you have a lot of space between the samples that you have. Why? This is important. Because if you develop algorithm on that particular small set of data, it will give you certain result, and for example, you can have, let's say, accuracy of that classification, let's say 96%. But when you put the same algorithm in a real life situation, the best scenario would be that it didn't sample something which is between your samples. But it almost never occurs like that. The danger is that once developed algorithm is put in use, is deployed, it almost always drop in accuracy, because inevitably that algorithm will face some samples which are not in your dataset. It will exactly try to sample something which belongs to blind spot. And those blind spots are actually completely empty parts of the dimensionality space and variable space which you want to probe. Let me summarize. You develop something on a certain small data set which is highly dimensional, and it gives you a good result. You report that, you celebrate, it is 96% of accuracy. Then you put it in real life use, and you actually have something completely different, because usually when put in real life use, those algorithms have much lower accuracy. Sometimes it is a little bit over 50%, meaning that you should have almost the same result with tossing the coin about anything. What is the solution for this? First of all, from statistical learning theory, there is one cure: collect more data. This is the first one. Second, try to reduce the dimensionality of the problem, because if you have higher dimensionality problem, you have large blind spots, and then with increasing the number of variables, they scale exponentially. Meaning that the only thing that you can do beside this, when you develop algorithm after deployment, you have to constantly monitor it and adjust it to new data sampled. So this is probably behind epic failure of Watson in oncology, because it was IBM's algorithm which was developed to advise for therapies in oncology. Alas, they developed algorithm on something which is only few sources of cancer on pretty small data, and what the advices that people got from that algorithm was completely inaccurate and dangerous. This is why they closed it. You can find Alan Turing Institute report, as well as an excellent piece from Wired, and also very important publication about internal inquiry about the reasons why Watson failed from 2018. There is also one very interesting paper published last year by Berisha et al. 2021 about theoretical explanation why this is so. I highly recommend to anyone who is aiming in developing any kind of algorithm in health to read this in detail to prevent future disappointments. Let's say that we shouldn't be so optimistic about all of this, because we need to know that AI algorithms are good for narrowly defined tasks. We don't have general AI and probably won't have it either in the future. So please try to be rational. I know that we need some solution for this area, but you need to be realistic about the real performances if you really want to make a change. So I hope that with time people will realize that AI is not perfect, neither the only resource that we can use, and we need more rigorous science which is accurately reported. Thank you for listening.